In Thomson's cathode ray tube experiment in 1897, he fired these cathode rays, these mysterious rays from a cathode toward an anode. He discovered that these cathode rays were really beams of negatively charged subatomic particles. But there was one thing that he found that led him to that conclusion. One calculation that he made that led him to the conclusion that they were negatively charged subatomic particles. That was the charge to mass ratio. He found the charge to mass ratio of these cathode rays to be 1.76 times 10 to the 11 coulombs per kilogram. What was special about that number? It was really big. And if that number, 1.76 times 10 to the 11, that's the important one right there, right? The exponent. If that's so big, then that must mean this number is so small. And if that number is so small, in fact, smaller than the mass of any other atom, then these particles that provided us with this cathode ray, this greenish glowing thing that nobody really knew what they were, they must be subatomic particles. That's the discovery of the electron. Now, Millikan comes along almost 10 years later and finds not the charge to mass ratio, it's already been done. He finds the charge of the electron. And he does that by his oil drop experiment. His oil drop experiment consists of two charged plates. Yesterday, we said the top plate was positive and the bottom plate was negative. Today, we're going to reverse it. Today, we're going to make the top plate negative and the bottom plate positive. I just want to show you that it doesn't really matter which way we have the plates oriented. It works the same basic way. We inject these tiny little oil droplets in between these plates. Some of these oil drops will be positively charged. Some of these oil drops will be negatively charged. Let's look at the negatives for a second. The negatives experience two forces. What are they? Gravity, which acts down, and the electric force, which acts, no, it acts down. Yesterday, the electric force acted up. Why did the electric force act up yesterday but acting down today? Because they switched the plates. Does that make sense? Yeah. So pay attention to that. Okay, usually we see the top plate positive, but there's no reason why we couldn't do this with the top plate being negative. Just that force is going to be in the opposite direction on the negative. Let's take a look at the positive particle now. This one experiences a force of gravity downwards. What about the electric force? Upwards. So yesterday, the electric force on this one was downward. Today, it's upward. If we're going to get one of these particles suspended, not moving, then which one's it going to be? The negative or the positive? The positive. Yesterday, it was the negative because they were the ones that had forces in opposite directions. Now, just because these are in opposite directions doesn't mean they're going to balance. It doesn't mean that they are going to be the exact same value and therefore cause this particle to be suspended. But it could happen. At least it's possible. It will happen if Fe equals Fg. Well, it'll either be suspended in that case, or it'll move up or down at a constant speed. In other words, it won't accelerate if these two forces are equal. Okay, if it is suspended or it's moving up or down at a constant speed, we're going to set those two forces equal to each other and then replace Fe with Qe, Fg with m times g, rearrange and solve for Q. We get mg over E. Now, every once in a while, we may have to replace E, the electric field between these two plates, with an equation. Which one would I use? Delta V over delta D. Good. Find the charge. Okay, find the charge. Maybe you're not looking at a charged particle that's suspended or moving at a constant speed. Maybe you're looking at one that's accelerating, whether it's the green one that's accelerating or the blue one that's accelerating because either Fg or Fe is bigger than the other one. In that case, we're going to say F net is equal to the sum of the forces, Fe plus Fg. Ma is equal to Qe plus m times g. And then, of course, once you plug in your numbers, you're going to worry about signs, what's positive and what's negative. Fg is going to be negative all the time. Fe is going to be negative here, but it's going to be positive here because it's downward here and upward there. So this one can either be positive or negative depending upon the situation. Make sense? Okay, you had 4 questions for homework. The first 2 We're on page 763. Any issues of those two questions, please, on 763? No, those ones are right. Okay. So the number isn't an issue, but the direction is. Okay. So let's take a look at number 2, focusing not on the number that we get there, but rather the direction of the electric field. Let's draw it out. This is what I suggest you do all of the time. All of the time. Okay, whether you're trying to find the direction of the field or not, it's probably a good idea to draw it out. But especially if you're trying to find a direction of something, draw it out. We've got an oil drop here that is positive, because it says it's plus 2e. It's positive. We have a gravitational force downward. Which way does the electric force have to be here? Upward. Otherwise, it wouldn't be suspended, right? It has to balance the gravitational force. If the electric force is upward, then which way does the field have to be? A positive particle experiences a force in the same direction as the field. What if it was a negative particle? Which way would the field have to be? Downward, because a negative particle experiences a force opposite to the direction of the field. Make sense? Okay. Draw it out. It becomes a lot easier, I think. So take the extra 20 seconds and do that. Second set of homework you had was on 764. This one and this one were wrong answers. So what I want to do is I want to go over both of these questions. First one says, what's the net force on a charge minus 5e? This mass, electric field is upwards. Let's see here. We've got an electric field upwards. We've got a negative particle that will experience a force of gravity down. Which way is the electric force on this negative? Shana, which way is the electric force on this negative particle? The electric field is up. The force is down, opposite to the field, right? Because it's a negative particle. Nope. But they tell me in this case it's up. So the field is opposite to the force. If it's a negative particle, it's in the same direction as the force if it's a positive particle. Okay, let's do the whole net force thing. It's equal to Fe plus Fg. We're not looking for the mass or the acceleration, I should say this time. So let's just set F net equal to Q times E plus M times G. Q is 8 times 10 to the negative 19, 5 times the elementary charge. We're going to drop the negative there because we never plug a negative into a sign of a charge into an equation, never. E is 1 times 10 to the 5. We add to that the mass, 2 times 10 to the negative 14 times 9.81. We do have to worry about positives and negatives at this point, though, because we plug numbers in. This one's going to be negative because it's a downward force. This one's going to be negative because it's a downward force. It's not negative because it's a negative charge. It's negative because it's a downward force. When we calculate those numbers and then we add them together, tell me what we get there. I think it's 2 point something. .7 times 10 to the negative 3 newtons. Is that okay? That's a negative force, so that means it's a downward force. Yeah. Shannon? It's the term that's negative in the equation, Q times E. And why is it negative? Because it's a downward force. We're not plugging in negative for the charge there. We never do that. We never plug in a negative sign for a charge. Okay, we plug in a negative for a direction. And that force is downward. So that force, QE, has got to be a negative value. Not the charge, the term. Now it works out to be the same thing here, but some other time it might not be, right? You might have a negative charge, but the force might be upward in some other case, in which case we make it a positive value, right? Yep, the electric field is up, the force is opposite to the field, so it's downward. And since the force is downward, we're going to make the force negative. We're not adding fields here, remember, we're adding forces. Yeah, the answer is negative because both forces are negative values. Makes it a downward force, right? And look at it. Two downward forces. What does that give you for a net force? A downward force. Okay, let's take a look at question 2 now. This time we're reversing the direction of the electric field. So this time the field is going to be downwards. It's a negative particle still. That means the gravitational force is downwards and the electric force is upwards. Can we set those two forces equal to each other? Only if it's suspended, does it, or traveling at a constant speed. Does it tell me it's suspended or traveling at a constant speed, Pete? No, so we can't set them equal to each other. If they are equal to each other, then we're going to calculate A, and it will be 0. It means we've done a little bit of extra work that maybe we didn't have to do, but that's okay. Okay, we don't know that they're equal right now. We don't know that it's suspended, so we have to assume that it's not. Let's say F net is equal to Fe plus Fg. This time we're looking for acceleration, not F net. So we sub in m times A. Let's solve for Q here. Okay, the mass was 2 times 10 to the negative 14 times A. The charge was 8 times 10 to the negative 19 times E, 1 times 10 to the 5. And the mass again was 2 times 10 to the negative 14 times 9.81. Gravity is negative, right? So we're going to make it a negative value. It's downwards. What about the electric force in this question? It's positive because it's up. When we calculate that force, that acceleration, I believe when we do the math there, it works out to be 5.8 or neg 5.8. Is that right? Oh, okay. So did anybody get 6? 6.0? If you get 6, you use this number, 1.2, but really that's a rounded number. Okay, so we want to use whatever this works out to be divided by 2 times 10 to the negative 14 should give me neg 5.8, I think. Emil? No, because it doesn't appear in every term. It has to appear in every term, not just both sides. Neg 5.8, yeah, okay, thank you. Okay, let's pull open the calculator then. Guys, just focus up here, okay? Let's do the right-hand side, 8 times 10 to the minus 19 times 1 times 10 to the 5. Let's subtract from that 2 times 10 to the minus 14 multiplied by 9.81. Now let's divide that by 2 times 10 to the negative 14. Then we get neg 5.8, yeah. Yeah. No, it's a negative value. If it's a negative value, it means it's down. So you get two forces, one's up, one's down. Which one's bigger? Gravity. Gravity's bigger because it's accelerating downward. Yeah, 5.8 down or 5.8, neg 5.8, either one. Yeah. Let's shift gears a little bit. It's almost chemistry that we're going to do for the next few minutes. Almost. An isotope is a version of an element. There's about 110-ish different elements. You see that on your periodic table. Okay, 110 different types of atoms, roughly. But each of those elements has different versions associated with them. Okay, carbon, for instance, has a number of different isotopes, a number of different versions. Carbon always has 6 protons, right? Always. But sometimes it might have 6 neutrons, and sometimes it might have 7 neutrons, and sometimes it might have 8 neutrons. Uranium always has 92 protons, but sometimes it might have 143 neutrons. Sometimes it might have 144 neutrons, sometimes 145, sometimes 146 neutrons. Okay, there's different versions or different isotopes of elements. we have to have a way to describe those different versions or those different isotopes of elements. We're going to use what we call isotope notation. This is not something that you're likely to see as a standalone question. Okay, you're not likely to see a question that says, well, describe this nucleus. Okay, how many protons does it have? How many neutrons does it have? So on. Rather, it's more of a tool to help us to do other things like the main focus of today's lesson, which will be, in just a couple of minutes, radioactivity. We have to go through this isotope notation to get there, though. A, in this case, sorry, this is backwards. X, in this case, doesn't really matter what we had there. X, in this case, is the symbol, the element symbol. So for carbon, for instance, that would be C. For uranium, that would be U. For lithium, it would be Li. For sodium, it would be Na. For chlorine, it would be Cl. Okay, it's the symbol for the element. Z stands for the atomic number. And the atomic number is the number of protons. Carbon always has 6 protons. Uranium always has 92 protons, and there's no exceptions to that. The number of protons is fixed for a particular type of atom. If we change the number of protons, we're not changing the isotope or the version of the element, we're changing the element into something else. An isotope always has the same number of protons, but a different number of neutrons. A describes the number of neutrons. We call that the mass number. It's the number of protons plus the number of neutrons. Carbon might have a mass number of 12, or it might have a mass number of 13, or it might have a mass number of 14. Uranium might have a mass number of 235. It might have a mass number of 238 or 239. But carbon always has an atomic number of 6, and uranium always has an atomic number of 92. How many protons in uranium again? 92. How many protons in carbon? How many neutrons in this particular isotope of carbon? 8. 14 minus 6 is 8. How many neutrons in this one? It's going to be 146. 146 neutrons. You can do that with your calculator, right? 238 minus 92 equals 146, right? This is the second easiest question in the history of physics. The first easiest question is, Mr. Dickie walks 5 meters in a time of 5 seconds. What's his speed? That's the easiest question. Here's the second easiest question in the history of physics. How many neutrons are contained in gold 197? How many protons, first of all? 79 protons. How many neutrons? 182 neutrons? Where'd that come from? 197 minus 79, right? Is that easy? Okay, so I wasn't lying when I said it was the second easiest question in the history of physics. Pretty easy, right? I'm going to give you about 30 seconds to answer these questions. All right, if we don't have any trouble with this, let's move on to the real point of the day. The real lesson for the day, which is radioactivity. Okay, we're just going to use what we just learned for isotope notation as a tool. Okay, radioactivity is the real point of the day here. Radioactivity is a natural process. It's a random process. What do we mean by that? A natural random process. It's not determined. We don't determine it. It's not man-made. We don't cause it. We don't control it. We have no say over it, whether it happens or whether it doesn't happen, when it happens or when it doesn't happen. We have absolutely no say or control over this whatsoever. It's completely natural. It happens on its own, and it happens when it wants to happen. It's a natural process. It's a random process in which a nucleus decays into another nucleus. Now, this is big. A nucleus decays into another nucleus. In chemistry, You talk about the rearrangement of electrons, sharing electrons, swapping electrons, chemical reactions that take place. When that happens, you might change one compound, maybe carbon dioxide, into something else. But it's still carbon and it's still oxygen, just rearranged. When we're talking about nuclear physics, we can actually change the carbon into another element. And we can change the oxygen into another element, not just rearrange them to form different compounds. That's radioactivity. Okay, it's a natural random process whereby something like carbon changes into something like nitrogen. The resulting radiation is ionizing. What does that mean? What's an ion? A positive or negative charge. It's a charged atom. So ionizing radiation can cause atoms to become ions. It can cause neutral things to become charged things. Now, that might not seem like a big deal, and sometimes it isn't, but sometimes it is a big deal. If you have ions floating around inside your body that aren't supposed to be there, because something ionized atoms, then you're going to get chemical reactions taking place inside your body that aren't supposed to take place. And that's not good. Biology is really just chemistry, right? Biology of the body results from chemistry of the body. Chemical reactions that take place between things that lead us to certain biological structures. If you have chemical reactions taking place that aren't supposed to be taking place, then all of a sudden we're going to start having strange things taking place in our body that we're not expecting, they're not supposed to be taking place. Things like sickness, things like cataracts in your eyes, things like cancer, things like death to the extreme. If we have ionizing radiation doing these things, ionizing atoms that aren't supposed to be ionized, then strange things start happening. We end up being poisoned effectively by radiation. There are three types of radioactivity that we're going to talk about today. The three types you can see are alpha, beta, and gamma. Alpha decay involves releasing an alpha particle. The atom, the nucleus, I should say, is really big. It's kind of cumbersome. It's not stable. A chunk of the nucleus breaks off. That chunk is the alpha particle. I often think of it as like an iceberg. The iceberg is the nucleus. There's a little chunk of the nucleus, a little chunk of the iceberg in the corner that breaks off and falls into the ocean. You still have an iceberg left over, right? You still have a nucleus there. Largely, the iceberg is still there. The nucleus is still there, but the nucleus has changed. The iceberg isn't the same as it was before. It's changed into something else. The chunk that broke off is the alpha particle. Okay, that's not the radioactive material. That's the chunk that breaks off of the radioactive material. It's a little piece of ice that breaks off of the iceberg. Now, sometimes you see an alpha particle symbol written like this, 42He. What do you think that means? What's He? It's helium. Yeah, it's helium. Helium consists of 2 protons and 2 neutrons, at least a helium nucleus does. So does an alpha particle. So really all we're talking about here is an alpha particle is just a helium nucleus. They're exactly the same. They're indistinguishable from one another. This is, by the way, not the kind of helium that you're breathing in, okay, when you fill up a balloon with helium and talk in a funny voice. This is helium nuclei. That's helium gas, which consists of helium atoms. It's much, much different. Helium nuclei are ionizing. They can cause some serious, serious radiation damage inside your body. Helium atoms can't cause radiation damage. They're not radioactive. Okay? They're not radioactive, and they're not ionizing. Okay? You can suffocate because you fill your lungs with helium, but you're not going to die of radiation poisoning or of cancer. Beta particles are one more type of thing that can break off. Another piece of the iceberg that breaks off, a smaller piece of the iceberg that breaks off. The symbol for a beta particle is 0 minus 1 beta. 0 minus 1, then it's a Greek letter beta. If, that is, we're talking about beta minus decay, there's also something called beta plus decay, or beta positive. How many protons, by the way, in an alpha particle? 2. How many neutrons? 2. So really it consists of 2 protons, 2 neutrons, just like a helium nucleus. How many protons and neutrons in a beta? It is a trick question. Yes, it is. Good for you. -1 protons? What's 0 mean? 0 protons and neutrons? There are no protons, there are no neutrons. What's the -1 mean? It's an electron. So we could also write it as 0 minus 1e. That's a little odd. Okay, that should seem a little puzzling to you. We got a chunk of the nucleus that breaks off. Okay, a chunk of the iceberg breaks off. What do we expect that chunk to be? Ice, right? A chunk of the iceberg breaks off and we look at it and all of a sudden it's like, oh, it's cake. How do we get a chunk of cake breaking off of a chunk of ice? Cake isn't present in ice. How do you get a chunk of cake breaking off? How do we get an electron breaking off a nucleus? The nucleus doesn't have electrons. How do you get an electron breaking off a nucleus when there were no electrons there? We'll talk about that in a second. It's kind of rhetorical. We'll talk about that in a second. What's this one? 0 plus 1 beta. How many protons? Nope. 1 proton? Nope. 0 protons. This 0 means 0 protons, 0 neutrons. There are no protons, there are no neutrons. What's the +1 mean? This is what we call a positron. This is the antiparticle of an electron. It's antimatter. How many people have read the book Angels and Demons or saw the movie? They talk about antimatter bombs and angels and demons. When matter and antimatter come together, they annihilate each other and they produce energy. Now, it couldn't happen in the way that it happened in that book and in that movie, but the idea, the basic science is correct, that when matter and antimatter come together, they release a whole lot of energy. Matter and antimatter are the exact same as one another, except for one property, and that's usually charge. An electron is the exact same thing as a positron, except the positron is positive. Positron is not a proton. It has the mass of an electron, but it has the charge of a proton. Let's go to gamma. 0, 0, gamma. How many protons? How many neutrons? Good. No protons, no neutrons. How many electrons? None. How many positrons? None. So what is this? Well, it's not nothing. It's electromagnetic radiation. It's not matter or antimatter, it's electromagnetic radiation. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. How do we say gamma rays are produced in the last unit? You looked at that, you guys heard that song, right? The YouTube song? A couple of times you heard that song. How were gamma rays produced? By nuclear decay. Today we're going to talk a little bit more about that nuclear decay that produces this electromagnetic radiation. Let's go back to alpha particles for a second. When does that chunk of the iceberg break off? Well, to understand that, we have to understand the details, the inner parts of a nucleus. There's 3 forces that act within the nucleus. 2 of them are really important for this. One is an electric force. That's the easy one, because we're familiar with that. Electricity can be repulsive or attractive. In the nucleus, it's always repulsive, always. Protons repel protons. Protons don't attract neutrons, by the way, not by the electric force, because you have to have a separation of charge to have positive attracting neutral, right? We can't have that in a neutron. So protons repel protons. There's also an attractive force in the nucleus called the strong nuclear force. The strong nuclear force causes neutrons to attract neutrons and protons to attract neutrons. So there's an attractive force and there's a repulsive force. If the attractive force is bigger than the repulsive force, then the nucleus stays together. If the repulsive force is bigger, then the nucleus breaks apart. Chunk of the iceberg breaks off. So far, so good. There's about 2,500 different isotopes or versions of elements. There's about 110 different elements and about 2,500 different versions of those elements. The vast majority of them are not stable. 2,300 are not stable. They're radioactive. Largely, that's because the repulsive force inside wins out over the attractive force that's inside, and the nucleus breaks apart. Alpha decay occurs when you have big nuclei and you have too many protons. Too many protons. That causes too big of a repulsive force. Not enough of an attractive force, too big of a repulsive force. The nucleus breaks apart. Yep. Chunk of the iceberg breaks off in an attempt to make it more stable. We get rid of a couple of protons. We also get rid of a couple of neutrons, but it does change the ratio of neutrons to protons to a more favorable ratio. So you got a better chance of being stable here. There's no guarantees. A lot of times once this happens, it's still radioactive, but it's closer to being stable. You get too many protons, too strong of a repulsive force, the nucleus breaks apart by kicking out an alpha particle, a helium nucleus. That occurs with big nuclei. Beta decay can occur with big or small nuclei. That occurs when we have too many neutrons. Too many neutrons? How can you have too many neutrons? Don't they cause an attractive, strong nuclear force? They do. That should make it even more stable if you have too many neutrons. The problem is, if you have too many neutrons, the nucleus is energetically unfavorable. It's not in a good energetic state. It's in an energetically unfavorable state. So the nucleus can't stay together then either. There's a really, really fine balance to strike here. You get too many protons, alpha decay can occur. You get too many neutrons, beta decay can occur. You got to have just that right ratio. You got to make sure that you maximize the attractive force, but you don't want to make that attractive force too big because it won't be energetically stable and it'll still break apart. You get too many neutrons. Now here's the crazy thing that happens. You get too many neutrons, what do? Well, you don't give off a neutron. Beta particle is not a neutron. What you do rather is change a neutron. A neutron is actually converted to a proton and an electron. Something that's neutral becomes something that's positive and negative. The proton stays behind because protons are a part of the nucleus, so it just stays there. You end up with one less neutron in the nucleus, one extra proton in the nucleus. The electron leaves because we don't want them in the nucleus. Electrons don't belong in the nucleus. The electron that leaves is the beta particle. It's like a club, the nucleus club. Who's in the nucleus club? Protons and neutrons. All of a sudden, we decide one day we have too many neutrons in the nucleus club. We like neutrons, but we get too many of them. So what do? You know what? We don't want to get rid of one. We don't want to kick out a neutron because we like them. Let's change them. We get too many neutrons. Let's change them. Let's change them into a proton. But we can't just leave them as a proton because that would violate the law of conservation of charge. A neutron changes into something that was positive. Well, we got to make an electron as well then. A neutron changes into a proton and an electron. That fills the law of conservation of charge. Neutral becomes neutral. But the electron doesn't belong in the club. So the electron gets kicked out. Proton stays behind, the electron gets kicked out. What happens here? What happens here? Once again, we have too many protons, but a different thing happens as a result of too many protons. Here we get too many protons. What does the president of the Nucleus Club say? We got too many protons. Let's change a proton into a neutron and a positron. Can't be an electron That wouldn't make any sense, right? Neutral and negative makes positive. It has to be neutral and positive makes positive. Change into a neutron and a proton. Sorry, a neutron and a positron. The positron leaves, right? Just like the electron left. The neutron stays behind because neutrons are allowed in the nucleus club. It's the electron and the positron that leave. No? Okay. Finally, we have gamma decay. Gamma decay occurs as a byproduct of some other type of nuclear reaction. When that happens, the nucleus is left in an excited state. But it goes back to normal. As it goes back to normal, it releases a photon, and that photon is a gamma ray. You've just seen a neutron change into a proton and an electron. You'd be excited too. The nucleus is left in an excited state. What happens? It wants to go back down to its normal state, and as it does that, it gives off a gamma ray photon. We're talking about two properties of each of these types of radiation, each of these types of ionizing radiation. First one we're going to talk about is the penetrating power. What that means is the ability of these types of ionizing radiation to go through matter. The ability to penetrate matter. The penetrating power, again, is the ability of this to penetrate matter, to go through matter. They have varying degrees of penetrating power. The last column is ionizing potential. That's the ability to ionize matter. They all have the ability to ionize matter. They're all ionizing radiation. Some of them are better at it than others. The good news, alpha particles have a very, very low penetrating power. It's 1 or 2 sheets of paper. If you fire alpha particles at me because one day you get mad at me and decide you want to shoot me with an alpha particle gun, then I will just take out my alpha particle shield, which is my booklet of papers here, and it will shield me just fine from those alpha particles. In fact, my clothes will shield me just fine from the alpha particles. They have a very, very low penetrating power. Beta particles, whether they're beta plus or beta minus, have a slightly higher penetrating power, well, significantly higher, but it's still relatively low in the grand scheme of things. It's about 1 to 2 centimeters of flesh. So they would go through your skin. Alpha particles won't. They'll be stopped by your skin. Beta particles will go through your skin, but they're not going to get to the inner workings of your body if you're exposed to them. Gamma rays, on the other hand, will penetrate several centimeters of lead. They have a very, very high penetrating power. No. Gamma rays are used in cancer treatment. You see them in a lot of places, including cancer treatment. They're used on purpose in cancer treatment because they're ionizing radiation. They can kill cells, including cancer cells, and they have a high ability to penetrate matter. In other words, they'll go through your body easily, and they'll attack that tumor that's inside your body easily. Now, the downside is they also attack healthy cells on the way through, okay, but they focus them in a way so that they're attacking mainly the damaged cells, the cancer cells. Now let's look at the flip side of all this. Alpha particles, although they have a very low penetrating power, have a very high ionizing potential. They have a hard time getting inside your body, but if they do, watch out. Gamma rays have a very high penetrating power. I don't want to say they have a very low ionizing power, but it's the lowest of the three. And beta's just fence sitter, right? Beta says, you know what? I kind of want to penetrate matter. I kind of don't. Beta says, I kind of want to ionize matter. I kind of don't. They're the fence sitters. They're in the middle. If you had to be exposed to one of these things, what would you want to be exposed to? It depends. It all depends upon context, right? Sometimes it would be most advantageous or least disadvantageous to be exposed to gamma. Sometimes it would be least disadvantageous to be exposed to alpha. It just depends upon context. The real danger with alpha and beta, by the way, is not so much being exposed to the particles right here. The real danger comes from consuming the material that is radioactive. So not the alpha particles per se, but the particles that produce the alpha particles. If you consume that because your water supply is laced with it, or the soil is laced with it, and the crops you grow end up being radioactive, then what happens is it starts decaying while it's inside your body. So then it doesn't have to penetrate matter because it's already in there. Yep. Tinfoil would protect you from alpha particles. No, not from gamma rays. Well, if you had a lot of tinfoil, I guess it would, but it would take a lot of tinfoil. Lead is really, really dense. So that's why we say lead, because lead is really good. I mean, compared to most other things, it's really good at protecting you from gamma rays, right? I mean, enough tinfoil would, sure. I mean, in the end, enough air would protect you from it. It just has to be a lot more air, right, than it does lead. Sorry? Yeah. It's a trade-off. It's a trade-off. Yeah, don't eat the lead. The last thing here is I want to describe the reactions that are taking place, these radioactive decays that are taking place. We're going to describe them by equations. We call them nuclear equations or transmutation equations. Transmutation is a process whereby one element is converted to another. That can happen by any one of a number of means, including radioactivity that we just talked about. Radioactivity is one way we can change an element into some other element. And we're going to describe these conversions, these transmutations, by use of an equation. They're not, in some ways, unlike a chemical equation. Chemical equations describe what's going on. We try to balance things out and so on. But nuclear equations, same thing, except that we're not trying to balance elements. We're trying to balance protons and neutrons. In chemistry, if you got 6 carbons on one side, you got to have 6 carbons on the other side. That's not the case in nuclear physics. Carbon's been converted to nitrogen. You don't have to you don't have to conserve carbon like you do in a chemical reaction. In a nuclear reaction, you have to conserve mass numbers and atomic numbers. And if that sounds confusing, trust me, it's easier than balancing chemical equations. Let's look at an example, and you'll see how easy it really is. First one says, write the nuclear decay equation for the transmutation of radium-226 undergoing alpha decay. So we get 226-88 radium undergoing alpha decay. If it's alpha decay, then alpha is a product, right? The chunk of the iceberg breaks off. What do we start off with? A big iceberg. What do we end up with? The little chunk of the iceberg that broke off plus a pretty big chunk of iceberg, but a little bit smaller than what we started with. What do we have here? Well, we have an alpha particle plus a pretty big nucleus, but a little bit smaller than we started off with. How much smaller? Well, if we had 88 protons over here, then we have to have 88 protons over here. 2 plus 86 equals 88. If we had a mass number of 226, then we have to have a mass number of 226. 4 plus 222 equals 226. How do we figure out what element that is? Periodic table. 86 is Rn, radon. Told you that's easier than chemistry. Much harder to balance a chemical equation than this one, isn't it? Let's try another one. Write the nuclear decay equation for the transmutation of lead-214 undergoing beta decay. By the way, this should really say beta negative decay or beta minus decay. If it doesn't say whether it's beta minus or beta plus, we'll assume beta negative. Okay, but it really should say. We got lead-214. Where does the beta minus particle come up here? Is it on the left side or the right side? The right side. It's broken off, right? It's a chunk that's released. 0 minus 1 beta. We call this a parent nucleus. Okay, it starts off this way. This would be a daughter nucleus. Okay, it's produced from the parent. 214, well, 0 plus 214 gives me 214. Minus 1 plus what equals 82? No, not 81. 83. And that, if you check your periodic table, is bismuth. Wait a second. Hey, wait, this doesn't make sense, right? We had 82 protons, now we have 83 protons. Does that make sense? It makes perfect sense because in beta minus decay, remember what happened? A neutron changed into a proton and an electron. So if we had 82 protons, now we've got to have 83 because we made one. Now, I'm sorry to have to do this to you, Brooke. It does get a tiny bit harder for beta decay. There is also another little particle that's produced here called an anti-neutrino. An anti-neutrino as represented by the Greek letter shark tooth. No. Neutrinos and antineutrinos were hypothesized in the year 1930 by a guy named Wolfgang Pauli. Okay, he looked at this, Pauli. He suggested that there was some missing energy here. In this reaction, there was something missing. The beta particle in the bismuth couldn't account for all the energy. So he hypothesized that there had to be some other particle existing here. He called those two particles neutrinos and antineutrinos. At the time, there was no evidence to support that at all, other than, look, there's missing energy. There has to be something. Years later, we've observed neutrinos and antineutrinos. So we know that that's the case now. We know that he was right. There is an antineutrino produced with beta minus decay. And by the way, if you have beta plus decay, there's a neutrino produced. No, it's just neutrino. Yeah, it was meant to be a dash. No. A neutrino is the shark tooth without the little line over the top of it. Easy enough? The only real trick here is that we either have a neutrino or an antineutrino added in. So the neutrino and the antineutrino, it's not logical in the sense that, we have to add them to balance it out, but they do have to be there. Okay? We can't just add up the numbers and say, oh, neutrino or antineutrino. But if we remember that they go with beta minus and beta plus, then it's not so bad. Let's take a look at another one here. Complete the following nuclear reactions. Well, this one doesn't tell me whether it's beta minus or beta plus. Let's figure it out. 30 plus what equals 30? 0. 16 plus what equals 15? Minus 1, what's that? Beta particle. Anything else? An antineutrino. 234 plus what equals 238? 4. 90 plus what equals 92? That's an alpha particle plus. Anything else? Nope. Last one. 13 plus 0, 6, sorry. Yeah, that's right. Yep. 6 plus 1, that's beta plus. That would be neutrino. Not an antineutrino, but a neutrino. For beta minus or beta plus, yes. Yep. One more example. Skip that one. Let's go to this one. These are what we call artificial transmutation equations. These aren't true radioactivity because it's not a natural, spontaneous process. We're making it happen. Instead of the iceberg breaking apart naturally, a chunk of the iceberg just naturally breaks off, we're making it happen. We're hitting the iceberg with something. We're crashing the Titanic into the iceberg. We're going to break off a piece of the iceberg because we've banged into it with a rock or a Titanic or something. Here's the iceberg. Here's the Titanic. It breaks apart. What does it break apart into? Well, 14 plus 4 is 18. 17 plus 1 is 18. 7 plus 2 is 9. 8 plus 1 is 9. What's that? What's 1, 1? Hydrogen. 1 proton, 0 neutrons is hydrogen. Or you could have just said 1, 1p because that would be a proton as well. It's a hydrogen nucleus or it's a proton. 105 plus 0 is 105. 48 plus minus 1 is 47. This is not beta decay. Be careful. This is not beta decay. Because beta decay involves a beta particle being produced, not being absorbed. We would call this electron capture, actually. Don't worry about the name of that. This would be silver, if you check your periodic table. And there is no neutrino or anti-neutrino produced because, again, the beta particle is not being made. The beta particle is being captured by the nucleus. You get about 8 minutes to work on the questions that I already assigned, questions 1 to 6 on page 767. In addition, you're going to have a couple more questions that I'd like you to do, please, on page 799, no, sorry, 800 and 803. There's 3 questions there. There's 1 question there, and there's 6 questions here. These will be done. You can get these ones done in the next 30 seconds. So that basically leaves you with 6 questions to work on over the next 8 minutes of class and for homework tonight. That's it for today.